So we were talking last time about degrees, minutes, and seconds, and operations with angles. Anybody have any questions about that? Okay. So then what I want to do is I want to review, we've talked kind of briefly, I remember what we have done. The spring break in here has been kind of hectic. We haven't really reviewed the parts of a circle yet, have we?
Well, I mean, we talked about the distance between.
Yeah, we just talked about angles and stuff like that. So that's where I want to start today. Is I want to start talking about parts of a circle. Now the first few here you should know. The single most important part, defining part of a circle, pretend that's a circle by the way, is of course that distance from the center of the circle out to the edge of the circle, which is called the radius. And that is actually one of the two features that define a circle. A circle is defined by its center and its radius, because every point on the circle is, of course, that distance from its center. Now, there are some lesser known features, like a segment that connects two points on the circle is called a chord. A chord that goes through the center is called diameter. And there is a relationship between the radius and the diameter. Diameter, of course, is equal to 2 times the radius. Or radius is equal to half the diameter. The distance around a circle is called its circumference. The circumference is found using that mythical pi times diameter, or 2 times pi times radius. We had to go over that so that we knew the radians and degrees equivalents. Well, those are the main parts of a circle that we use. There are some other parts that are going to be just as important to us. They're a little bit lesser known. Sure. Yeah. If we have a line that touches the circle but doesn't go into it, that is called a tangent. It's possible for a line to be tangent to a circle. It's also possible for two circles to be tangent to each other. They just touch surfaces, but they don't intersect. They don't go into penetrate each other. A line that cuts through the circle is called a secant. Now, there are all sorts of alternative definitions of a secant. Some will define a secant as a chord that's been extended to go outside the circle. The actual technical definition of a secant is any sort of a line or a segment that contains points that are both inside the circle and outside the circle. So that's where the secant falls.
It's only if it doesn't go through the center.
Now, if it goes through the center, it can still be a secant.
Okay. It has to go all the way through, though. It has to have one.
It has to have parts of it in the circle and parts of it out of the circle. This blue line that I just drew in is a diameter. That's what we're going to refer to as a reference diameter. A reference diameter is usually horizontal. For our purposes, it will always be horizontal. And it's used to reference different points and features of the circle. One of those is something called a sign. A sign is a distance from any point on the circle to that reference diameter. So if I pick this point here, the sign of that point is the distance from that point to the reference diameter. That'll always be measured at a perpendicular. Distance from a point to a line is always measured on a perpendicular. So that distance is the sign of that point. That's not the only sign. Every point on the circle has a sign. This point here has a sign. That distance is going to be the sign of that point. That distance there is the sign of that point. There's another point over here that has the exact same sign as this one, because it's the same distance above the line. These points down here are said to have a negative sign because they're below the line, below that reference diameter. As we start to look at our trig functions, we need to look at something called a unit circle. Once again, pretend that's a circle. A unit circle is a circle with a radius of 1 unit. Whether that's 1 inch, 1 centimeter, whatever. It is 1 unit of measurement, whatever unit you are using. I'm going to go ahead and draw crosshairs through that circle. Pretend those go through the center. This is often, it actually originated from the navigational compass rose on a map. The east direction here is defined to be 0 degrees. And that is what is referred to as the initial side of an angle. Remember we mentioned how that direction is, the difference in direction is one of the ways we define angles between two rays. Well, that direction starts here at 0 degrees. That is the initial side of any directional angle. And then if we draw our angle up here, let's say this is 60 degrees. That is the terminal side. So the angle starts here, goes to there. We're talking about something called coterminal. Because this is on a circle, we're not limited to just going from 0 degrees and wrapping around to 360. We can actually keep going. So if we look at this terminal side here, unless we're given more information, we don't know if that's really 60 degrees or a complete turn plus another 60 degrees, 420 degrees, right? 360 plus 60. Or it could be 2 complete turns, 307 or 720 degrees plus another 60. It could be 780 degrees. Or it could be 3 complete turns. We just keep going. Let's see, that would be what, 1140 degrees. It would be 3 complete turns plus 60. All of those angles will have a terminal side where that yellow line is. In fact, we could have started here and gone backwards 300 degrees. So a negative 300 degrees would also be coterminal. It's going to end in the same spot. So what we tend to talk about is something called the simplest coterminal angle. By simplest coterminal angle, I mean it's going to be between 0 degrees and 360 degrees. So if I give you 754 degrees, and I ask you to find the simplest coterminal angle, what I'm asking you to do is to unwrap that from around the unit circle to figure out where it ends up. Now mathematically I can do it by just subtracting 360. I subtract 360 from 754 and I will get what? 394 degrees. Is that between 0 and 360? No. It means I can subtract 360 again. 394 minus 360 is 34 degrees. Now that's between 0 and 360. Or if you're given negative 428 degrees, and you're asked to find the simplest coterminal angle. Well, that one's negative, so I'm going to unwrap it going the other way. Instead of subtracting 360, I'm going to add 360. 428 degrees plus 360 is still a negative 68 degrees. So that means I am going to add 360 again, which will give me a positive 292 degrees. So the simplest coterminal angle there will be 292 degrees. Make sense? Yeah.
Okay, so I get that your 360 is the highest you can go, but it can be by a different number in between or not?
You will always add or subtract 360 to get up or down.
Okay.
Yep. Because you have to unwrap a full turn, and a full turn will always be 360 degrees. The other way you could look at these is look at it as having your circle here. It's like the 754. Here they say, okay, here I am. I got 0. There's 360. 720. How much is left? Well, another 34 degrees gets me to my terminal spot. Or I could go, okay, negative 360. I have to go another negative, what, 68 to get there. So now then I would still have to do a little work here. It's 360 minus 68 gives me the 292 to get at it from the front side, but still. Does that make sense? No? It can be. And for some people that are visual, they like to do that. Basically, all it is add or subtract. If it's below 0, add 360 till you get positive. If it's above 360, you subtract 360 till it's below 360. So if you're given 1200 degrees, you're going to have to subtract 360 to get to 640 degrees. You're going to subtract 360 again. Is that right? No, that should be 840 degrees. Subtract 360 to get to 840 degrees. Subtract 360 again to get 480 degrees. Subtract 360 again, gets you to 120 degrees. You're now between 0 and 360, so you stop. If you have negative 910 degrees, you're going to go the other direction. You're going to add 360. Adding 360 once gets you to a negative 550 degrees. Adding 360 again gets you to a negative 190 degrees. Adding 360 again will get you to a positive 170 degrees. So now you're between 0 and 360, so you can stop. Now there are things about this unit circle that are going to define our angles. Oops. Define our trig functions. A lot of people think trig is about right triangles, and we do apply it to right triangles, but as I've mentioned, trig is about circles. It gets applied to right triangles through those similar triangles. But let's go back to that 60-degree angle here. That's the terminal side of that 60-degree angle. It defines a point on the circle. The sine of 60, now this is a unit circle, which means this radius here is 1 unit. The sine of 60 degrees is the sine of that point on the circle, which is just going to be that distance. So that's how those trig functions are defined, as actually dimensions on this circle, as we create those angles and look at their terminal side and the point it defines on that circle. And we're going to look at that more next week. But for right now, I want to use this unit circle to define another way of defining angles. We could define this 60 degrees. Rather than defining it as 60 degrees, we could describe it with the length of the arc it traces out on the unit circle. Did you guys do arc length calculations at all last semester? Okay. An arc length is found by first finding the total circumference of the circle. So that has a radius of 1, right? So its circumference is going to be 2 times pi times that radius of 1, which comes out to be 2 pi. I'm going to leave it as 2 pi, and I'm not going to simplify it to be 6.28 for now. Because generally when we're talking about this, we leave it as 2 pi. That's the whole circumference. The arc length is then found by taking that circumference times the fraction of the circle. The fraction of that circle is this central angle here divided by 360. So for this, it's going to be 2 pi. That's theta. That looks like an O with a line through it like that. That's the symbol for an unknown angle.
No, I just wasn't sure if it was a symbol or if you were just...
Oh, that is a symbol. So for this, we would put in 60 degrees there. 2 pi for circumference, 60 degrees for our angle. I'll put 2 pi over 1 here. 2 pi times 60 is 120 times pi. 1 times 360 is 360. Both 120 and 360 can be divided by 120. So that's going to be 1 pi, or just pi. 360 divided by 120 is 3. So it's pi over 3, or 1/3 pi. That arc length is pi over 3 units. That is defined to be pi over 3 radians. That is an alternative way of expressing an angle by putting it in radians instead of degrees. So a 60-degree angle is equivalent to pi over 3, or 1/3 pi radians, because the arc length on the unit circle that is defined by that 60-degree angle has a length of pi over 3, or 1/3 pi. The easiest way to deal with radian measure is look at a complete circle. A complete circle is how many degrees? 360 degrees, right? As we defined up above here, on the unit circle, a complete circle is 2 pi radians. That's the whole distance around. So what that's telling us is 360 degrees is equivalent to 2 pi radians. Some books will actually divide out the 2, and they'll write it as 180 degrees is equivalent to pi radians, which is fine. It's probably a little easier to use. I always remember it as a complete circle is 360 and 2 pi. So if I want to convert angles, let's say I want to convert 30 degrees into radians. We're going to do this just like we did our measurement conversions. I have 30 degrees. I'm going to put it over 1. Did you guys do conversion factor conversions? You think so? Okay. I'll show you an example. In a conversion factor conversion, let's say I tell you that you have 99 rods. And I want to know, or 99 rods, 99 feet, to put it that way. And I want to know how many rods that would be. And I tell you that 1 rod equals 16.5 feet. So to make that conversion, technically you set up 99 feet over 1. You're going to multiply by a conversion factor where you're going to put feet on bottom so they cancel out. Rods on top. 1 rod is 16.5. The feet cancel out. You've got 99 rods over 16.5, which divides out to be 16 rods, or 6 rods, I should say. Look familiar? Okay. Same thing's going to happen over here then. We're getting rid of degrees, so degrees are going to go on bottom, and we're going to radians. So radians on top. 2 pi radians equals 360 degrees. Degrees are gone. It's easier for me to divide them out and reduce, or multiply them out and reduce. 30 times 2 pi is 60 pi radians. 1 times 360 is 360. And now I see that both 60 and 360 divide by 60. 60 divided by 60 is 1, so that's 1 pi, or just pi. 360 divided by 60 is 6. So that's pi over 6, or 1/6 pi radians. Does that make any sense? A little? Let's do one more example, then we'll have you guys try a couple. 135 degrees. Let's convert it to radians. So 360 degrees to go on bottom. 2 pi radians on top. The degrees cancel. 135 times 2 is 270. And that is pi radians. 1 times 360 is just 360. Both 270 and 360 can be divided by 90. 270 divided by 90 is 3. I still have the pi there and the radians. 360 divided by 9 is 4. So that's 3 pi over 4 radians, or 3/4 times pi radians. Now have you guys in your notes try 120 degrees and 45 degrees. Convert those into radians. Yeah, 270 and 360 can both be divided by 90. That's the largest number they can both be divided by. You could start out, you could have started out saying, okay, we got 270 and 360. I just isolate the numbers. we'd say, hey, they can both be divided by 10. So we'll divide by 10. So that's 27 over 36. They can both be divided by 3. So you divide by 3. Now you got 9 over 12. You can divide by 3 again. And then just put the pi and the radians back in it once you reduce the numbers. I often will leave the radians off of it just to make it easier. So the degrees cancel out. 240 pi over 360. They divide out by 120, so yeah, 2 pi over 3 radians. What you got for that one? Perfect. For 45, okay, I'll wait for you. So, yeah, 45 over 1 times 2 pi over 360. The degrees cancel. 45 times 2 is 90 pi over 360. Divide by the 90, it's pi over 4 or 1/4. Simple enough. What if we're going the other way? What if I give you 5 pi over 6 radians? I want to convert it into degrees. We take 5 pi over 6. Now we're going to put the 360 on top. We want to convert 2 degrees. We'll put the 2 pi on bottom. Now the pi is going to be the first thing that cancels out. 5 times 360 is 1800. 6 times 2 is 12. 1800 divided by 12 is 150 degrees. Again, a lot of times I just drop the radians off there to make it easier to do the calculation. Or, let's say we do 7 pi over 12. What are we going to multiply by? We're going into degrees, so the degrees will be on top. And the 2 pi's on bottom. Pi's cancel out. 7 times 360 is 2520. 12 times 2 is 24. 2520 divided by 24 is 105 degrees. Make sense? The 24 here? 12 times 2.
Oh, it's cross both down.
Oh, yeah. You just multiply straight across here. So, let's have you try pi over 2 radians into degrees. And should be pi over 4 radians into degrees. That's a 4.
Is it 90 and 135?
This one's right, yeah. So this one here, I'm going to just ignore the radians. 2 pi on bottom, 360 degrees on top. The pi's cancel out. So I've got just, this is a 1. I just got 360 degrees on top. 2 times 2 is 4. So 360 divided by 4 is 90 degrees. Here I'm going to multiply. The 360 goes on top because I'm going 2 degrees. Getting away from radians, so my 2 pi goes on bottom. Technically this is 2 pi radians. The radians cancel out. So the pi's cancel out. 3 times 360 is 1,080 degrees. 4 times 2 is 8. It divides out to 135 degrees. One of the reasons why radians is useful is it's useful for angular distance. Just to come up with a pretty cheesy example here, let's say I have an object swinging on a string. I just got a weight out there and I'm swinging it around. This string is 6 feet long, and I'm swinging it around. And I want to know if I swing it through an arc of 60 degrees, how far does it swing? In other words, what's this arc out here? Well, if I'm using degrees, I've got to go through that arc length calculation. We have to find the circumference first. So that circumference is going to be 2 times pi times that radius of 6. That's going to be 12 pi. And so then the arc length is 12 pi times the 60 degrees over 360, which comes out to be 2 pi. So that length here is 2 pi feet. So 2 pi is 6.28. That's 6.28 feet. However, if instead of using 60 degrees, if we had used pi over 3 radians, we could have found the arc length when we're dealing with radian measure is simply the radius times the angle. We have a 6-foot radius times pi over 3. 6 times pi over 3 is 6 pi over 3, or 2 pi, or 6.28 feet. Make sense? So for when we're talking about angular distance or distance around the circle, if the angle is measured in radians, it's really easy to find that length. It's also angular velocity. Let's say this is spinning at like 200 RPM, right? And it is, again, we've got a radius here of, oh, let's go with 4 feet for a radius. Well, 200 RPM, remember, each is revolutions per minute, right? So I can write that as revolutions over 1 minute. Whenever I have a rate, it can be written out as a fraction like that. But 1 revolution is 2 pi radians, correct? So the revolutions cancel out. I have 200, and of course it's 1 on bottom here, just 1 minute. 200 times 2 pi, that's 400 pi radians per minute. So that rate, 200 RPMs, is 400 pi radians per minute. So if I want to convert that from an angular velocity into a linear velocity, the linear velocity is simply that angular rate, 400 pi radians per minute, times my radius of 4 feet. .400 pi times 4 feet is 1600 pi feet per minute. 1600 pi, 1600 times 3.14 is 5024 feet per minute. So when we measure angles in radians, there are a lot of calculations when we start dealing with circular motion that become a lot simpler. And so there are some huge advantages to getting used to dealing with radians. For you guys, it'd be more so in machining, where they're dealing like turning on a lathe and stuff like that, where they'd be looking at RPMs to surface cutting speeds and stuff like that. But it's still, there's some useful things. And for you guys, you can look at cycles. You know, your electricity goes through 60 cycles a second, or 3,600 cycles a minute. And you can think of that as being a radial velocity to figure out how many cycles it goes through in a given period of time. Okay, for now, I've got a new sheet I'm going to give you. In that other packet, by the way, there's page 537 through 538. Exercise 25-4, 1 through 15, the odd. Talk a little bit about radian and angular conversions. This next one I'm going to give you, though, is a little bit better at it. This is page 323 that I'm going to hand out to you. And if you want to do 1 through 47, the odd here.
Do both these packets?
Yes. This is just the one page. This is out of the packet you already have, and this is going to be a page I'm going to give you now. And remember, there is no class tomorrow because I'm in meetings, so this is kind of doubling up your homework a little bit. Take a good look at the word problems though on this worksheet, because there's some really interesting problems that make you think about angles.
What do you say? No. Okay, then no. I mean, if you want to.
But some of those questions, like, you know, if you wait 20 minutes, how many degrees have gone by on the clock? They're kind of good exercises to think about actually what they mean by rotation and degrees and stuff like that. Okay, I'll let you guys have the last 9 minutes to get started.